Welcome! In this explainer, we're going to break down something pretty amazing, the single, elegant framework that AI uses to solve an incredible variety of problems. And I mean from something as simple as a child's puzzle, all the way to planning a trip across the entire planet. So let's kick things off with the big question that's going to guide us through this whole discussion. How on earth can the exact same AI principles that figure out a little sliding puzzle also plan out a super complex, multi-stop flight itinerary across the globe? It seems impossible, right? But the answer is actually surprisingly elegant.
To get to that answer, here's the roadmap we're going to follow. First, we'll look at the foundational framework that AI uses for basically any search problem. Then, we'll see how it works with simple toy problems, before moving on to much more complex, real-world examples. We'll compare the two, and then we'll wrap up by talking about why this one single approach is just so incredibly powerful.
Okay, let's dive right in. The absolute key to AI's incredible versatility in solving problems is something called a standardized mathematical framework. Now, this isn't just some vague set of guidelines. Think of it more like a universal language, a formal structure that lets us define almost any challenge in a way that a computer can understand and start working on. You see, every single problem that an AI can search for a solution to, no matter what it is defined by these 5 core components. It all starts with the initial state. That's just the starting line, right? Where are we at the beginning? Then you have the actions, which are all the possible moves the AI can make from any given state. The transition model is basically the rulebook. It says, if you're in this state and you take this action, you will end up in that new state. The goal test is simple. It's what tells the AI, you did it, you found a solution. And finally, you've got the path cost. Think of this as the scorecard. It measures how good a solution is. Maybe that's the shortest distance, or the lowest price, or just the fewest moves to win.
Now, let's see how this 5-part framework actually works in a nice, controlled environment. And to do that, we're going to look at what AI researchers call toy problems. These are essentially the training grounds, the gyms where algorithms get tested and fine-tuned before they're ready for the real world.
The most important thing to get about toy problems is that they aren't meant to solve a real issue. Nope, their whole purpose is to provide a clean, simple, and perfectly defined little universe. This lets researchers test and compare how different search algorithms perform without all the messiness and unpredictability of reality getting in the way. It's like a perfect laboratory for AI. A classic example is the vacuum world. As you can see in this diagram, the problem is defined perfectly. A state is simply the robot's location, is it in room A or room B, and the cleanliness of each of those rooms. The actions are super simple: move left, move right, and suck up dirt. And the goal? Totally unambiguous. All rooms have to be clean. It's this perfect self-contained universe for testing out an AI agent. And here's another famous toy problem, the 8 puzzle. In this case, a state is defined by the exact location of each of the 8 tiles, plus that one blank space. The only available actions are to move that blank space up, down, left, or right, which effectively slides another tile into its place. The goal, as you can see, is a very specific, ordered arrangement of those tiles. The rules are simple, but as you're about to see, the number of possible states is anything but. So get this, that simple-looking 8 puzzle has over 181,000 unique configurations it can be in. And what's really wild is if you just double the dimensions to a 15 puzzle, that number explodes to over 10 trillion states. This really shows you why even a toy problem needs an intelligent search strategy. You can't just stumble upon the solution by guessing.
This is such a great example of flexibility. The 8 queens problem, which is all about placing 8 queens on a chessboard so none of them can attack each other, shows that you can frame the exact same problem in different ways. You could formulate it incrementally, where you start with an empty board and add 1 queen at a time. Or you could do a complete state formulation, where you start with all 8 on the board and just move them around to fix the attacks. These different approaches can lead to wildly different levels of difficulty for the search.
Okay, so we've seen how this all works in the neat, tidy world of puzzles. Now let's move on and see how this framework scales up to solve the complex, messy problems that people actually care about, the ones whose solutions really impact our daily lives. And this is where we see the big jump in difficulty. Unlike those tidy toy problems, real-world challenges are messy. Their state spaces, that is, the set of all possible situations, can be absolutely vast, constantly changing, or even infinite. They have to account for so many more variables and a whole lot more uncertainty. Let's think about a perfect, everyday example. Your phone's GPS. This is a classic route-finding problem. In this case, the states are specific locations like cities or intersections,
just like you see on this map. The actions are driving along the available roads. The AI's job is to search through all the possible paths to find the one with the lowest cost, and that cost could be time, distance, or even fuel consumption.
Now, airline travel planning takes this a giant step further. At its heart, it's still a route-finding problem. But as this diagram shows, the path cost isn't just distance anymore. It's this complex calculation involving flight times, seat availability, layover durations, and constantly changing prices. The goal is also much more personal. Are you trying to find the absolute cheapest flight, the fastest one, or maybe the one with the most comfortable seats?
Robot navigation is on another level of complexity altogether. A robot, like the one you see here, isn't just hopping between predefined points on a map. No, it's operating in a continuous physical space. That means there are literally infinite possible locations and angles it could be in. The AI has to constantly process sensor data to deal with unexpected obstacles and even potential errors in its own measurements, which makes the whole problem incredibly dynamic.
So I think it's really important to pause and just nail down the key differences between these two types of problems. When you see them side by side, the huge leap in complexity becomes crystal clear.
And this table just lays it out perfectly. The purpose shifts from simply testing an algorithm to actually providing a useful solution. The state space goes from small and perfectly defined to massive and often continuous. And the level of abstraction totally flips. Toy problems get to ignore all the messy details, while real-world problems, like autonomous driving, have to account for things like physics, time, and totally unpredictable events.
Okay, let's bring this all home and talk about why having this single, standardized 5-part framework is so fundamentally important to the entire field of AI. This is really the heart of the matter. This quote is really the key takeaway of our entire discussion, because we can abstract any problem, whether it's an 8 puzzle or something as complex as designing a new computer chip, into the same basic structure of states, actions, and goals. We can then apply the same powerful search algorithms to solve them. It's this universality, this power of abstraction, that makes AI so incredibly adaptable.
And that leaves us with a final thought to chew on. We've seen how this one framework can handle everything from simple puzzles to planning routes across planets. So, as we face new and even more complex challenges in science, logistics, and exploration, you have to wonder, how will this fundamental approach to problem solving continue to evolve and help us find the solutions of tomorrow?